So, enzymes, what they are, mostly proteins. There are some RNA molecules that work as enzymes, but for our intents and purposes, mostly proteins. Then, what they do, the main goal is to increase the rate of the reaction. Now, how they do it? Every reaction can be schematically represented this way. So you have reagents and you have products. And each of these have certain energy levels. So this is the energy of reagents, this is the energy of products. So you may think, oh, okay, so we just go from top to bottom. It's not that simple because you have to go over a hump. And this hump right here is called activation energy. Okay? So the higher the activation energy, the slower the reaction is. And you, for instance, when you, I don't know if it ever occurred to you, but you never probably asked why paper doesn't burn. Like if you put the paper on the table, why doesn't it burn? Why do you need to, provide the flames first and then it will burn by itself? When you provide flames first, you provide energy to get over the hump. Does that make sense? So, what's interesting, the hump, the activation energy, becomes smaller in the presence of enzymes, so they reduce activation energy, but they do not influence the overall outcome of the reaction. So, they have no effect on the ratio of the product. Does that make sense? Good? So if we want to kind of represent how, quote-unquote, enzymes work, so here we have an enzyme, let's say it's this, the enzyme. Enzyme interacts with the substrate. And then the reaction goes on. And what you have in the end, you have the enzyme remaining intact. And slightly separated from the enzyme is the product. Okay? Now, what's important to understand? Enzymes help to get from point S to point P, from substrate to product. So enzymes are not wasted in the reaction. They come out of the reaction unchanged. Does that make sense? And they are extremely specific. You can see I deliberately put that substrate so it matches the shape. So far we good? Any questions? It's just general review, okay? Cool? Now there are a couple of types of enzymes, general categories that I want you to be aware of, because first, clinically very important actually, are Exo Enzymes versus Endo Enzymes. So what's the difference? Well, Exo Enzymes produced by bacterial cells and released outside of the cell. Endo Enzymes remain in the cytoplasm. The enzymes that we talked about so far, like DNA polymerase, RNA polymerase, ligase, they all are Endo Enzymes. Does that make sense to you? Now, what is the clinical importance? Well, the clinical importance of Endo Enzymes, if you have enzymes that are produced within the cell that, for instance, can destroy antibiotics, they will convey antibiotic resistance to the cell. Exo enzymes, even more important clinically. Think of it this way. If you have an enzyme that can destroy connective tissue, does that make sense? If this enzyme is released outside of the cell, you boned. Connective tissue is going to be destroyed. The example of such enzyme, collagenase of Clostridium perfringens, is the enzyme that destroys tissues in gangrene. Coagulase of Staphylococcus aureus is the enzyme responsible for clotting problems in people with sepsis. Okay, we talked about Staph aureus infections and scalded skin syndrome. Exfoliating toxin is the enzyme that destroys basement membrane. All those are examples of exo enzymes. Does that make sense? Good? Okay. Now, second sort of broad two categories of enzymes. Constitutive versus regulator. So constitutive enzymes are produced at the same level all the time. This is very rare, really. Not a lot of enzymes are doing so. Most of enzymes are regulated, okay? And there can be several layers to that regulation. So first, we're going to talk about if the enzyme is already produced, how can you regulate the enzymatic activity, okay? So you can regulate it via inhibition. So enzymatic inhibition can be of two types, competitive and non-competitive. So competitive inhibition is when an inhibitor binds to the active site. So this is the active site of the enzyme. This pocket here that I pictured is the active site of an enzyme. So inhibitor binds at the active site. Let's say, let's say Julianne and I, so she represents the substrate, I represent the inhibitor, right? And the chair right there represents the active site. In case of competitive inhibition, whoever comes there first wins. Does that make sense? If she's there, I can't bind. But if I'm there, if I'm in place of substrate at the active site, that's it. Does that make sense? In non-competitive inhibition, also known as allosteric, chemical binds to an allosteric site. So allosteric means, allo means different, steric means space, another space. Okay? That makes sense? So say if John is substrate and I'm an inhibitor and that chair is an active site, I'm not getting into that chair. I'm getting there in the adjacent one and somehow make the active site inaccessible. I change the shape of them, something happens. Does that make sense? So basically allosteric inhibitor will bind somewhere here, completely like screwing up the active site. Are we clear? So just like there can be allosteric inhibition, there can be allosteric activation. Okay? Now in case of allosteric activation, same story, activation molecule can bind to a different site. Okay? Make an enzyme workable. And that brings us to another concept, terminological mostly concept, of apo and holoenzymes. So some enzymes can't work until some kind of cofactor is available. So imagine that this blue angle is an enzyme, and we're going to call it apo enzyme. Apo enzyme is not functional. It can't do anything. Okay? But when a cofactor is present, cofactor can be an ion of a metal, okay? It can be relatively small organic molecule, what you end up with is a proper complex here, and this whole complex of cofactor and apoenzyme. Okay? This whole thing is called Holoenzyme. So in other words, apoenzyme remains dysfunctional until it binds a cofactor, and this whole system becomes a holoenzyme. Does it make sense? Good? Okay. Now, another concept, last concept about the enzymes, really small one, is that enzymes are usually organized in pathways. And in those enzymatic pathways, often the products at the end of the pathway will be regulating the activity of other enzymes. I should have told everybody that we're going to take like 5 minutes to go to the restroom. So imagine that you have several intermediates, A, B, C, and final product T, okay? Are we clear? Each step here is regulated by the enzyme 1, enzyme 2, and enzyme 3. Okay, so look what can happen. At the very end of that enzymatic pathway, the product D can inhibit the first enzyme. You see what I'm saying? So this pathway runs, product accumulates, and when it becomes like really common, the inhibition sets on. It's your typical negative feedback response. Okay? So it inhibits the pathway, the levels of D drop, there's no more inhibition, the process starts again. Does it make sense? So this, for instance, this D, check this out, this D might as well be a competitive or allosteric inhibitor of the enzyme E1. Does that make sense? So that basically makes sure that your cell doesn't overproduce certain chemicals or it doesn't run out of nutrients and so on and so forth. Okay? We good? Okay. 5 minutes. I understand that